prove that the set of integers is a countable set. Now whenever we have to prove that a set is a countable set, we have to define a mapping phi from the set of natural numbers to the required set. Right? And there should be a one-to-one correspondence between the set of natural numbers and that set. Then we say that this A is a countable set. Now because we need to prove that set of integers is a countable set, then we have to define a mapping from n to the set of integers. Let's start with the proof. Let's define a mapping phi from the set of natural numbers to the set of integers by phi of n is equal to, we have to consider the two cases for n if it is even or odd. So this is n divided by 2 if n is even, and it is negative of n minus 1 divided by 2 if n is odd. Because there should be a one-to-one correspondence between the set of natural numbers to the set of integers, we have to define such a phi for that. Now set of integers is what? It is from 0, 1, 2, 3, 4, so on, and negative 1, negative 2, negative 3, so on. This is a set of integers, and set of natural numbers is from 1, 2, 3, 4, so on. Now if I consider n to be equal to 2, what I am getting? Now for n is equal to 2, that is n is your even natural number. For n is equal to 2, that is when n is even, we have to put the value over here. So I am getting for n equal to 2 as 1. And 1 is your positive integer. Right? Let's take n to be as 5. So 5 is an odd natural number. So we put over here, that is, we are getting this to be as negative 2. So we are getting the negative integer. So can you see that there is a mapping between the set of natural numbers and the set of integers? For n equal to 2, we are getting a positive integer. For n to be as 5, we are getting a negative integer. Likewise, when you put the even natural numbers or odd natural numbers, you are getting your positive or negative integers, right? Phi is well defined. Phi is 1, 1. And phi is on 2. If we are able to prove all these results, we say that set of integers is a countable set for this mapping. So first one is phi to be well defined. What is the definition for a well defined function? A function is said to be a well defined. Suppose f is a mapping from x to y. If x1 equal to x2 implies f of x1 is equal to f of x2, where x1, x2 is belonging to the set x, which means one element of x has one and only one image of y, right? So for this mapping, let n is equal to m, and we have to prove that phi of n is equal to phi of m. Let's divide both the sides by 2, so we get n divided by 2 is equal to m divided by 2. If n and n are even, and if I subtract negative 1 from both these sides, I am getting n minus 1 equal to m minus 1. Let's also divide both the sides by 2 and also multiplying both the sides with negative 1. So this is if n and m are odd. Why I have done this? Because I need to prove phi of n is equal to phi of m, right? And you have noticed that this left hand side is nothing but your phi n, and this right hand side can be written as phi of m. So therefore, phi is well defined. Right? Okay. Next we have to prove that phi is 1, 1. What is the definition for a function to be a 1, 1 function? For that we have to start with the images. That is, f of x1 is equal to f of x2 implies x1 is equal to x2. Or if you start from the distinct points, if x1 not equal to x2, then f of x1 is also not equal to f of x2. Right? You can apply any of these definitions. So let me start with this definition. And for well-defined, we start from x1 equal to x2 and reach here. x1 equal to x2, and that implies f of x1 is equal to f of x2. This is a definition for well-defined function, and this is a definition for the 1-1 function. For a 1-1 function, we start from the images. For the well-defined function, we start from the points. Please be very careful with the definitions. So for a 1-1 function, let's start with phi of n is equal to phi of m. And I have to show that n is equal to m. This I have to show. By definition, what is phi of n? It is n divided by 2. So then, phi of n is n divided by 2. Similarly, phi of m is m divided by 2. This is for the even numbers. For the odd numbers, we write or. Phi of n is negative of n minus 1 divided by 2. And phi of m will be negative of m minus 1 divided by 2. So this implies if you cancel this 2 and this 2, you will get n is equal to m. And also for this also, if you cancel this 2 and this 2 and this 2, also the negative sign, and then cancelling the negative 1 also from the both the sides, we get n is equal to m. So for both these cases, we are getting n is equal to m. This is what we have to prove. So therefore, phi is 1, 1. Third one is phi is onto. This we have to prove. What is the definition for a onto function? If f is a function from x to y, then for every element of y, there must exist a pre-image in x. Right? We need to show this. N to z. So for every element belonging to z, there must exist its pre-image in n. Right? So let's take one element from z. Let x belongs to z. If x is positive, then there exists a natural number belonging to n such that phi of that natural number should be equal to this x. Right? We have to choose such a natural number so that I can get x. What is the definition for phi? How we have defined phi? We have defined phi to be as phi of n is equal to n divided by 2 for even numbers. Right? So I have to choose such a natural number so that I can get x. So if I take n to be as 2x, putting here 2x, I'm getting 2x divided by 2 as x. Right? So for even numbers, I'm putting here phi of 2x. So phi of 2x is equal to 2x divided by 2, that is equal to x. Second, phi of n is equal to negative of n minus 1 divided by 2 if n is odd. So I have to also consider the odd case too. So what value I take for the natural number? What natural number should I take from the set of natural numbers so that I can get phi of that natural number to be equal to x? So think about the natural number so that I can get here the value equal to x. Let's take n to be equal to negative of 2x plus 1. So phi of negative of 2x plus 1, this should comes out to be as x. So this is equal to. So for odd natural numbers, phi of n is negative of n minus 1 divided by 2. So phi of minus 2x plus 1 is equal to negative of, just put the value as here, n. That is minus of 2x plus 1 minus 1 divided by 2. So that is equal to this 1 will go, and we are getting positive 2x divided by 2, that is equal to x. So these are the two natural numbers for which I am getting x. But x was arbitrary. X was arbitrary. So for every x belonging to the set of integers, we are getting its pre-image in the set of natural numbers. For every element this is happening, right? Because we have taken x to be any arbitrary element. So writing here, but x was arbitrary, therefore every element of Z has its pre-image in the set of natural numbers under phi. So therefore phi is on 2. And because we have proved that phi is 1, 1 and on 2, so set of integers is a countable set. So writing this, since phi is a mapping from set of natural numbers to the set of integers, and this mapping is 1, 1 and on 2, therefore Z is a countable set. For the countable set, the mapping should be 1, 1 and on 2, right? Or there is a 1-to-1 correspondence between the set of natural numbers and the required set, right? Alright, thank you.